In this lecture, we are going to introduce embedded computer systems. We shall begin with a general coverage that seeks to outline what an embedded computer is. From the start of microprocessors, we can realize that there are two categories of applications of microprocessors. These are in general purpose computers and in embedded computers. Both the categories are computers. Therefore, in each we have a CPU, memory, and ports. These are constructed in such a way to suit the particular application. General purpose computers are those computers that are used for general purposes. We can think of such applications as word processing, accessing the internet, playing games, transaction processing systems, keeping of medical records, among other things. General purpose computers can run a number of different programs at the same time. In order to ensure that these programs do not interfere with each other and run efficiently, there is need of an operating system. An operating system is a set of software that manages the operation of a general purpose computer. This means that the software on a general purpose computer is made up of user programs and an operating system. General purpose computers have a lot of RAM. They use what is known as the von Neumann architecture. In the von Neumann architecture, both the program and data are stored in the same memory. In other words, they use the same address space. Storage on a general purpose computer is in the form of a hard drive, and nowadays we are seeing a drive towards the use of solid state drives as storage devices. General purpose computers have standard I/O ports that include USB ports, parallel ports, LAN ports, SD interface ports, Bluetooth, and Wi-Fi. These standard ports are used to connect to external devices that include keyboards, mice, and printers. General purpose computers have general purpose I/O devices. On a typical general computer, we have a keyboard, a video display unit, a touchpad or touch screen, or a mouse. The circuitry for the functionalities that are found on a general purpose computer are built onto a motherboard. This is a motherboard that is found on a typical desktop computer. We can see the CPU socket, the I/O connections, and memory slots. So those are examples of some of the circuitry that is required to be placed on a motherboard. Embedded computers are computers that are designed to control the operation of a piece of equipment or machinery. For example, to control a decoder, a remote control, a television set, a microwave cooker, a clock radio, or a washing machine. These are examples of items that we will find in a typical household. In the commercial sector, we can use embedded computers to control the operation of, for example, a drink dispenser, a photocopying machine, or a fuel dispenser. In instrumentation and control, we can have embedded computers being used in the measurement of variables in the plant or in the control of an automation system. For example, the control of a bottling plant. We can also find embedded computers being applied in aircraft. The instruments that we find in an aircraft can be controlled or run by embedded computers. For robots, we can have the function of the robot being controlled by an embedded computer. In ships, submarines in this case, you can find embedded computers controlling the operation of the ship. In traffic control, we can also make use of embedded computers. For example, to generate the sequence of traffic lights. And another example, to operate a boom gate. Embedded computers generally run one user program at a time. Therefore, there is no need for an operating system. The circuitry that makes up an embedded computer is usually built onto a small printed circuit board. The board is in turn built as part of the equipment or machine that is being controlled by the embedded computer. This is where the name embedded computer comes from. In general, for embedded computer systems, microcontrollers are used as the processors. Microcontrollers are programmable devices that have got the CPU, memory, ports, and various other peripherals all built onto the same IC chip. In other words, we can refer to them as computers on a chip. All these components are built onto the same chip so as to reduce the chip count. Most of the pins on a microcontroller are used as general purpose I/O pins. The I/O pins are used for connecting to I/O devices that include sensors, actuators, switches, symbol displays, among other devices. Here is an illustration of a typical microcontroller. We can see the various components that are inside the IC package. Typically, a microcontroller is a number of memory blocks. The first memory block is the program memory. Program memory is required to be involatile, hence it can be implemented as ROM, EEPROM, EEPROM, or flash RAM. Program memory is required to be involatile because after a program has been downloaded into the microcontroller, it is generally required to run for a long time before it can be changed. The second type of memory is the data memory. Data memory is used to store data and the configurations required for the operation of the microcontroller. Data memory is implemented as RAM because data can change at any time. A third block will be the stack memory. The stack memory can be implemented as a separate RAM block, or it can be implemented as part of the data memory. The fourth type of memory is a storage memory. This is memory where we would want to store items on a more long-term storage basis. It can be implemented as EEPROM or as flash RAM. The memory in a microcontroller generally uses the Harvard architecture. In Harvard architecture, we have different address spaces for the different memory blocks. The illustration shows the von Neumann architecture of memory. We can see that there's a block of memory where the program is stored, and then there's a block of memory where the data is stored. Both the program and data use the same address space. In other words, we cannot have the same address being used for both an item in the program section and an item in the data section. They will have to use different addresses. Here, for comparison purposes, here is the Harvard architecture. We have got, in this case, 4 blocks of memory, A, B, C, and D. Each of these blocks of memory starts at address 0. So we can have the same address being used in more than one of the blocks. However, depending on how we address the items in the memory, the address that we use will refer to a particular memory. So the blocks A, B, C, and D will be used for different purposes. For example, a block for the program, a block for the data RAM, a block for the stack, and a block for the storage memory. There are a number of microcontroller families and microcontroller manufacturers out there. In this slide, I've just given 3 examples of families. These are families of some of the most common and famous microcontrollers, and these are the Intel 8051 family, the manufacturer being Intel, the Microchip PIC series, the manufacturer being Microchip, the ARM series, the manufacturer being ARM. Then the illustration just shows typical images of members within each of these 3 families. We cannot start all the different microcontrollers that we have in the world in this course. So we are going to start only one microcontroller device. This particular device is the Microchip PIC 16F877. It was chosen because it has got a wide variety of features that we can liken to a large number of other microcontrollers. The fortunate thing is that once we start one microcontroller, the knowledge that we gain can be easily extended to other microcontrollers. Therefore, once you have studied this microcontroller, you can be able to start and use any other microcontroller from any other microcontroller family. Let's now highlight the features of the PIC 16F877. Let's begin with the digital I/O ports and on-chip peripherals. We have a total of 33 input-output pins. These are distributed into 5 ports. 3 of the ports have 8 pins each. One of the port has 6 pins, and the last port has 3 pins. We have an 8-bit wide parallel slave port. We'll see the details later on. We've got 2 8-bit timer counter modules. We have 1 16-bit timer counter module. We have 2 capture compare PWM modules. We have an 8-channel 10-bit ADC. We have 2 analog comparator modules. We have a USART module for serial communication. USART stands for Universal Synchronous Asynchronous Receiver Transmitter. We have a synchronous serial port capable for SPI and I2C serial communication. There is a total of 15 sources of interrupts on the PIC16F877. 2 of these interrupts are external interrupts. These are indicated by signals or changes of signals on the relevant pins on the microcontroller. The other 13 are internal interrupts. These are generated by on-chip peripheral modules. They are used to alert the need for attention after occurrence of a certain event or condition in the particular peripheral. The internal interrupts makes it a lot more convenient to run the on-chip peripheral modules. The PIC16F877 has a number of high-performance RISC features. RISC stands for Reduced Instruction Set Computer. This refers to a computer that has got a simplified instruction set so that it can operate and execute instructions faster and therefore give a high performance. For the PIC16F877, we have only 35 instructions. All the instructions are 14 bits wide, therefore they are of the same word size. If instructions have got the same word size, it makes it simpler to decode and execute them, and therefore it contributes to the performance of the device. The clock speed of the PIC16F877 is up to 20 megahertz. A fetch cycle takes 4 clock cycles to run, and an execute cycle also takes 4 clock cycles. In the PIC16F877, there is a 2-stage pipelining that makes the fetch and execute cycles to overlap. This results in a single instruction being executed in 4 clock cycles, which we can say is in one machine cycle. So this makes the instruction execution to be faster and therefore contribute to the high performance. The PIC16F877 has 4 memory blocks. These are the data RAM, which is implemented as RAM, the stack memory, which is implemented in RAM, the program memory, which is implemented as flash RAM, and the EEPROM data memory, which is implemented as EEPROM. The data RAM is seen as 8-bit registers that are called file registers. It has got a total of 512 addresses. 96 of the addresses are used as special function registers. The rest of the addresses are used as general purpose registers. Then some of the SFRs may be used as GPRs. The program memory is 14 bits wide. It has got a total of 8K entries of 14 bits each. It is used to store the program. It may also be used to store data as a storage area. The EEPROM has 256 bytes. It is used to store data on a more permanent basis. It is seen as a peripheral by the CPU. So in other words, it is not directly accessed by instructions in the microcontroller. It is accessed through some special function registers. The stack memory is 14 bits wide and it has got a total of 8 entries. It is not accessible by the programmer. It is only used to store return addresses after calls and branches to interrupt service routines. The internal architecture of the PIC16F877 can be modeled as shown. We can see that we've got all the peripherals and all the blocks of memory except the stack and program memory connected to a common data bus. This data bus also links to the CPU core. The CPU core is the one that is responsible for fetching and executing instructions. So the CPU core is connected to the program memory through another bus and also to the stack through another bus. So there are different buses for the different kinds of memory. The CPU core can in turn be modeled as an arithmetic logic unit, an accumulator known as a working register W, and a control unit. The ALU is responsible for the arithmetic and logic operations. The working register is responsible for holding one of the operands in 2 operand instructions, as well as storing the result of an operation in some of the operations. The control unit is responsible for the internal operation of the microcontroller. These images show the various forms of packages for the PIC16F877. We've got the PDIP, the dual inline package, which is a 40-pin package. We've got the QFN, TQFP, and PLCC. These are all 44-pin packages. What differentiates these is only the overall dimensions of the packages. And these are the overall dimensions of the packages that we've just shown. So depending on dimensions, one can choose the appropriate package for the application. Here is the pinout for the PDIP, that is dual inline package. It's a 40-pin package. We've got 40 pins. The core functions of the bulk of the pins are as digital input-output pins. But however, as can be observed there, we can see that most of the pins have more than one function. So each pin generally has got a number of multiplexed functions. The function of a pin will depend on what is connected to the pin, as well as the program that has been written to run the microcontroller application.